Welcome to example number 2. This is known as a conical pendulum. So imagine you have a tether ball. So maybe you've heard of tether ball before. It's just basically a string and a ball attached to it, and the ball is whirling around in this cone-like fashion. So it's moving in a circle, but it's if you can see this three-dimensional view, it makes a nice cone. All right, which we call a conical pendulum. It's a special type of pendulum. So when the ball is hit by, say, a paddle, then the ball will then be swinging along in this perfect horizontal circle with a constant speed v, and it's making an angle theta with respect to the vertical. The ball will take a time of t to make one revolution. The ball's mass is given as m, and the length of the rope is shown here as L. We're asked to find out the tension in the cord acting on the ball and the angle theta in terms of M and L and T for the tension, and theta probably in terms of these variables. Okay, it's quite a complex question here. So the first thing we would do is we would draw the forces that are acting on the ball. So ideally, I would draw the free body diagram for the ball when it's right over here at the furthest point so that we can easily see all the forces. So go ahead, maybe stop the video and draw all the forces that would be acting on the ball at this particular point. So hopefully you realize that there's a tension right along the string. We'll label that as F sub t. And we have a force of gravity acting straight downwards, and we'll label that as F sub g. And now let's choose our axes. I'm going to choose to put our x-axis in this direction right here, and then I'm going to choose my y-axis to go straight up along there. Now you might be wondering, why did I choose to put x towards the center of the circle in the plane of that circle? The reason for that is as this ball moves around in this nice horizontal circle, the acceleration towards the center is here, which is right along the direction of my x-axis. And so we're going to want to apply Newton's law, second law and first law along the x-axis, and we want to choose it conveniently in the same direction as the acceleration. So remember that the net force is acting directly towards the center of this circle, which is producing this centripetal acceleration. Okay, so now let's apply Newton's laws. Let's choose to apply Newton's second law along the x-axis. So we're going to sum the forces along our x-axis, which is equal to ma, and this a is really the centripetal acceleration. So the net force is equal to m times the centripetal acceleration, which is v squared divided by r, which I'll use a capital R in the picture because that's what's shown. Now, what force or forces is causing this ball to continuously move around in the circle? Well, you can't just say it's the tension by itself, because really the tension points both horizontally and vertically. It's the horizontal component of that tension. So I'm just going to rewrite that as F sub Tx. So we should show that in the picture. So this, I'll just make as a dashed line here. This is Ftx. That's the horizontal component of the tension. And right up along here, along our y-axis, right up to here, this is our y component of our tension. See, vertically, since the ball is not moving up or down and it's maintaining the same altitude, it's level in that plane, then the tension in the y component of that tension must balance out by gravity. So over here, I'll write maybe some of the forces in the y must balance out to give you 0, because it's not accelerating along my y-axis, it's actually remaining at rest. So the y component of that tension minus the force of gravity will give you 0. They're balancing each other out. So the y component of that tension equals Fg, which is equal to mg. So we need to rewrite the tension in the x direction and the tension in the y direction in terms of the tension, and I'll also use angle theta. Now you can see that this line here, dashed line here is parallel to my chosen y-axis. And alternate interior angles here would say that this angle is also theta. Let's redraw our tension down below, and let's make a triangle with our tension, our y component, our x component, and theta. So there's F sub t. I just drew it out here a little bit longer. And there's the y component of the tension and the x component of the tension. But I'm going to move this up to here now. And there's my right angle, and there's theta. And so what trig ratio would I use to find the tension in the x direction in terms of the tension and theta? Hopefully you're thinking sine. Sine theta is equal to opposite, which is the tension in the x direction, divided by the hypotenuse, which is ft. So rewriting for the tension in the x direction, we could write that as ft times sine theta equals mv squared over r. We could do the similar thing for the tension in the y direction. We would use cosine of theta, which is the adjacent side, fty, divided by the hypotenuse, which is ft. And so we can get fty, which is really the tension multiplied by cosine theta. And this is equal to Fg, which is really just mg. That's the weight, mass times the acceleration due to gravity. Okay, so now we want to get our tension in terms of m, l, and t. And I have a sine theta there, and I have a v, and I have an r. I have to get rid of a bunch of variables. Well, we do know that the velocity is given as the distance that it goes around a circle, which is the circumference, 2 pi r, divided by the time period t. So now we're going to use t into our equation at least. So our tension now is times sine theta equals m, and then we have 2 pi r divided by t quantity squared all over r. So then, just simplifying a bit, we're going to have 4 pi squared, that's 2 pi quantity squared, times an r squared times an m, and then the bottom will have a t squared and an r. And we can see one of these r's will cancel out here. Okay, well, we've got to get rid of r, and we've got to get rid of sine theta. There's some relationship between r and theta, and oh, we got to use L. Yeah, do you see this triangle right in here? Let me highlight it here. This is the triangle that I'm looking at right along there. This is L, and this is R, and this is theta. Is there a trig relation that you can relate L and R and use theta? See, R is the opposite side of this triangle, and L is along the hypotenuse. If you're thinking sine theta is opposite, which is R, divided by the hypotenuse, which is L. So therefore, R is equal to L times sine theta. And we're going to replace that down here. All right, so we have ft times sine theta equals 4 pi squared, but then let's replace R with L sine theta. And then this all divided by the period squared. And whoa, look at that. We got a sine theta on both sides. Whoa, that's nice. They can cancel out. So now our expression solving for ft will be just simply 4 pi squared. Oh, I'm missing an m here. Oh, there's an m there. I forgot to write it there. Times m times L divided by the period squared. That's the first part solved. So I'll just put a box around that answer, and that's a nice derivation of finding the tension in terms of the mass of the tether ball, the length of the string, and the time that it takes to make one cycle, squared in this case. Okay, so we also have cosine theta, and we can rewrite that by itself as cosine theta equals mg divided by the tension. But the tension is given over here as 4 pi squared. So we can write cosine theta equals mg all over 4 pi squared ml all over period squared. And interestingly, the mass cancels out. And so you get cosine theta equals, let's bring up that t squared to the top, t squared times g all over 4 pi squared times L. And so there's our answer for the second part. Now you're going to be seeing this problem possibly in a lab. It's important to notice the relationships here. For example, that tension in that string depends on the mass of the ball. If you make that ball heavier, you're going to obviously get more tension. And we also could kind of look at the angle as well. How could, if you were to say, keep the period the same, and you're still on Earth, keep g the same, but then make the length of the string longer, then that would mean cosine of theta would have to get smaller. There's all sorts of relationships that you can see through this, and we'll be examining this in more detail in a lab, hopefully. And that's it for this example.